This is the first video in Chapter 36 dealing with geometric optics and in particular mirrors. Let's define real or virtual images. A real image is one in which light actually passes through the image point, and so the actual light is involved in making that image. A virtual image is one in which the actual light does not pass through the image point, and so it's just a place where the image appears to come from, but it's not actually comprised of real light. Only real images can be shown on screens because the actual light would then form the image that you would see. Here's a flat mirror. We have an object in front of the mirror, this arrow, and we're going to look in particular at this point P. If we start at P, and a ray of light approaches the mirror, it's going to bounce off the mirror and come straight back. And so that reflection off the mirror is going to appear like it comes from somewhere behind the mirror. So if we follow that reflection back, we find a point, or at least a direction from which it appears to come from. Let's try another ray of light from point P, and we're going to have it reflect off the middle of this mirror. And it's going to reflect, and we'll prove later that the angle of incidence will equal the angle of reflection. So this angle that it hits with is going to equal this angle that it comes out with. And if we follow this reflecting ray back, it's going to appear to come from behind the mirror in some direction. If we take these two rays and follow them back, we find that they appear to come from a point behind the mirror that is actually the same distance behind the mirror as the object is in front of the mirror. And so we have an image behind the mirror that looks just like the object in front of the mirror, only it's going to have some kind of left to right reversal. But it will be located about as far behind the mirror as the object is in front. We're going to look at this a little bit more closely, but we're going to state that we have a sign convention for mirrors and for all optics. And this sign convention is that we'll define the object distance, P, as being positive if it is on the same side as the incoming light to a mirror or an interface or a lens or whatever. Whatever we look at in optics, the object distance is positive if it is on the same side as the incoming light. And the image distance, Q, is going to be positive if it is on the same side as the outgoing light. Negative if it's not. So it's a very simple convention, but it's something that we can apply to all the optics we're going to look at in this chapter, geometric optics. So not just mirrors. So keep this in mind, and it'll make the optics much more easy to deal with, especially the equations. So P is positive if it's on the side of the incoming ray of light. Q, the image distance, is positive if it's on the side of the outgoing ray of light. Let's try this for a flat mirror. In this case, our incoming ray is coming from the left here and going to the right, and our outgoing ray is staying on the same side as the object here. So, in this case, the image is as far behind the mirror as the object is in front. Our image distance is a negative P because P is going to be positive. Our object distance is on the same side as the incoming ray, so it's a positive value. But our image is behind the mirror, so it is not on the same side as the outgoing real ray. The outgoing real ray is on this left-hand side here. So our image distance is going to be negative, and it's going to, in this case, it's going to be equal to negative P. It's going to be the same magnitude value behind the mirror, but it's not on the same side as the outgoing ray. The image height is equal to the object height, And so we would have that the image height is equal to h, and our magnification is equal to 1. Image is upright. Well, more on this a little bit later. But the upright just means we have a magnification of positive 1. And the image is virtual. Because our image distance is negative, the image is going to be virtual, meaning it's not being comprised of real rays. The outgoing rays are not on that side where the image is. So it is a virtual image. And we have this apparent left to right reversal, but not up and down. So up and down it is strictly a true image, but left to right reversal to the side. Here's an application. Auto mirrors. Some auto mirrors have day and night settings. And with the daytime setting, you have light coming in, reflecting off the, going through a glass, refracting, and then reflecting off the mirror and coming back and refracting to your eye. So you're getting a direct image of the light during the daytime. But if you turn the mirror for nighttime, you don't really want to have all those brights coming straight into your eyes. So you turn the mirror, and your main beam is going to actually be reflected and refracted away from your eyes, and you're just going to pick up the one little reflection off this first interface of the glass. That's going to be a much dimmer reflection, but it'll be enough for you to see who's behind you. So because of the mirror being turned, you get the full-fledged reflection misses your eyes, but you get the weaker reflection, and allows you to see the person behind you at nighttime. Spherical mirrors. They have the shape of a segment of a sphere. A concave spherical mirror has the silvered surface of the mirror on the inner or concave side of the curve. A convex spherical mirror has the silvered surface of the mirror on the outer or convex side of the curve. Let's say you want to keep this straight. Here's a memory device for concave and convex. Let's say you had a cave, and it kind of has a feature of caving in. So we say it caves in, and if we had a con, we would say that this would be concave. Makes sense. So if it caves in, if the mirror caves in, it is concave. Here is a fortune teller trying to vex you. So with the crystal bar add a con, we have convex. See? Convex for the outer spherical surface, and concave for the concaved spherical surface. All right. Well, actually, the concave works, and then use convex for the opposite. Here's a concave mirror. Mirrored surface, and it's caving in. We have some center of curvature here, a radius of curvature. If you had an object, real rays from the object will converge at some point and then continue to diverge from that point. Let's say we had a ray coming in here to this concave mirror, and it's reflecting off the mirror. And if you were to focus in on that point where the ray is coming in and touching the mirror, then it might appear, at least in that locality, at least on a very local scale, that it's kind of flat there, and the angle of incidence will equal the angle of reflection in that sense. And so whatever ray is coming into that point is going to reflect out from that point, and in this case it's going to go through this point I and then continue to go on after that. Let's say we had another ray, and it hits down over here, and again, if I were to focus in real close locally on this mirrored surface where it almost appears like it's flat at that point, I would see that the angle that it comes in with is also equal to the angle it goes out with. And so it's just going to hit, come out, and in this case also converging at point I and then diverging from there. Where these two intersect is the location of our real image. This image is being formed by the actual rays of light, and so if you were to see and look at this point, it would appear like the actual object was at that point. The image is real. Spherical aberration. Let's say you had a concave mirror, and maybe it's perfectly spherical, which is probably not what you want, because as you get away from small angles, as it converges near that point, it's actually not going to be perfectly on that point. And so as you get away from small angles with this principal axis, which is the middle axis, the rays that make large angles from this axis will converge to points that are nearby, but not exactly at that image point. This will give you a blurred image as you're trying to look at this real image. We say that this is spherical aberration. One famous example of spherical aberration is the Hubble Space Telescope. It was put out in 1991. Billions of dollars invested into this telescope, and the first time they tried to look at image, they realized that some of the optics were not ground to specifications. They were not perfectly the way that they should have been grounded, and so we had some aberration in the images, and they were blurry. So this was repaired 3 years later through a very famous mission, and they applied some extra optics that allowed the Hubble Space Telescope to function as it was intended, and it's been one of the greatest inventions of humankind since then. Not too long from now, we will have the James Webb Space Telescope, which probably will take us even further down the road as the Hubble has done. And here are some of the great images from the Hubble Space Telescope. We are going to employ ray diagrams. Now, with the ray diagrams, we're going to show how the light is coming in to a optical device like a mirror. Ray 1 is drawn parallel to the principal axis, and it's going to come out, reflected back through the focal point F. More on the focal point later, but anything coming in parallel is going to be reflected back through this point, which we're calling the focal point. Ray 2 is drawn through the focal point, and as it reflects off the mirror, it's going to come out parallel to the principal axis, which is the middle axis to the mirror. Ray 3 is drawn through the center of curvature. Anything drawn through the center of curvature is on the radius of the curvature itself. Hence, it's going to hit exactly perpendicular on the mirror itself, and it's going to reflect right back on itself. So it's going to reflect right back, right through the center of curvature on its way back. Ray 4 is drawn to the principal axis vertex, which is right in the middle of the mirror, and the angle of incidence should equal the angle of reflection. So it will, if we treat that as, at least in a local sense, as being relatively flat at that point, whatever angle it comes in with is going to equal the angle it comes out with. We will use these kinds of ideas to construct a ray diagram. Let's try it with a concave mirror. We have an object, and we have a principal axis through the middle going to the mirror, and we want to reconstruct this object as to where its image is going to be. We're going to use these rays to show that. First ray is coming in parallel, and any parallel rays to a concave mirror are going to come out through the focal point. And even if you looked on it on a very small local level here, you would still see, at least normal to the surface here, that the angle of incidence equals the angle of reflection. But it's coming out through the focal point and diverging from there. Here's ray number 2 that's going through the focal point on its way to the mirror, and anything that does that is going to come out parallel to the principal axis. So if we have just these 2 rays, they're coming out, and we can see that this tip of this object is actually converging at a point down here. And that would be the location of the tip of the image. So I could actually show the image at this point as being in that location. So I really only need 2 rays to determine where the image is. That's pretty cool. If I had a light ray that came right through the center of curvature, which is the radius itself of the curvature, it's going to bounce straight on and bounce right back and come right back through that same line. And we can see that if we combine that with one of the other rays, that again we can locate, or even 2 of the other rays, we can locate where that image is. How about that? And there's a 4th one I can use. If I put a ray right through the vertex of the mirror, which is right at the principal axis, angle of incidence will equal angle of reflection coming out. And that's a 4th one that could be used with these other 3 rays, and it too converges right at that tip. So any one of these 4 rays, or any ray going into that mirror from that tip, will converge on that point, only these are the 4 easiest ones to use because their reflection is predictable. So the intersection of any 2 of these rays will help us set up where the image is. In this case, we have a real image. It is inverted. Our image distance is positive, but the magnification will be negative because we have an inverted image. Let's actually calculate this magnification. Consider 2 rays leaving the object below. One ray passes through the center of curvature and bounces straight back through the center of curvature. The other one is going to the vertex, and the angle of incidence will equal angle of reflection that's coming out. They are forming this image, H prime, for the arrow as we see it here, which is inverted. We can see from the gold triangle that we have a right triangle here with an angle theta right here. And the tangent of theta is equal to the opposite side, h, over this distance of the object from the mirror. So that is the object distance. So tangent of theta equals h divided by p. If you look at this little blue triangle, it is a similar triangle. It's got the same internal angles. It's also a right triangle with the same angle theta here. And if I look at the tangent theta there, I would have that it's equal to the opposite side, h prime, over this distance here from the image to the mirror. So that's going to be q. And it's inverted, so it's going to be negative h prime over q. Taking the ratio of these 2 equations, we would have that with a little bit of algebra, that the magnification is going to be equal to our h prime height over our h height as how our image compares to our object, and that will be equal to negative q over p. In this case, both q and p are positive quantities, so the magnification will be negative, and that's why we have an inverted image. P is positive because it's on the same side as the incoming ray. Q is positive because it's on the same side as the outgoing ray. Also note, from the same figure, if we look at alpha, we would have, let's look at this small triangle alpha right here. The tangent of alpha is going to equal negative h prime over this distance from C to I. And that's going to be equal to the radius of curvature of the whole mirror minus the image distance. And that will be that little distance right there. So that's going to be a negative h prime over r minus q. And looking at the other triangle alpha here, tangent of that alpha is going to be the opposite side h over this distance from the object to the center of curvature, which will be the object distance p minus the radius of curvature r. Bear with us, we're going somewhere with these geometries. We take the ratio of these two. Tangents alpha cancel out and give us 1 on the left hand side. And just rearranging just a little bit, we have that the radius of curvature r minus the image distance q over the object distance p minus the radius of curvature r is equal to negative h prime over h. But we just determined that that is equal to the magnification, and the magnification is equal to negative q over p. So we have a negative q over p. Negatives cancel out, and with a little bit of algebra we can proceed through these different steps, multiplying through, and then we'll divide and put all the q and p terms together, divide through a q plus p, and we have q plus p over p times q is equal to 2 over r. I could write that as, get rid of the q's on these terms and the p's on this term. Finally, I get 1 over p plus 1 over q is equal to 2 divided by r. So 1 over the object distance plus 1 over the image distance is equal to 2 over the radius of curvature of the mirror. How about that? This is one form of what is called the mirror equation. Consider this. If we take this mirror equation, and let's say the object is really far away from this concave mirror, then our object distance would be infinity, and 1 over infinity would be 0. So using this mirror equation in that case, we would have 1 over infinity for 1 over p, and that would be 0. So we simply would have 1 over q is equal to 2 over r. So the image distance would be equal to the radius of curvature divided by 2, which means that anything infinitely far away, hence having parallel rays coming into this mirror, are going to converge at a point that has half the distance of the radius of the mirror to the center of curvature. We define that point where these parallel rays that come in from an object far away converge on a point. We call that point the focal point. So where parallel rays converge is where the focal point is, and in this case it is half the distance of the radius of curvature. So the focal length is the radius of curvature divided by 2, and if we substitute this in to our mirror equation, then we have this nice equation. 1 over the object distance plus 1 over the image distance q is equal to 1 over the focal length for the mirror, where the focal length is equal to the radius of curvature divided by 2. And here's an example. We have parallel rays coming in to this mirror here, and they're all converging on a point which happens to be half the radius of curvature of the mirror itself. And that distance of that point to the vertex of the mirror is the focal length. So let's take a look at a concave mirror. Here's a concave mirror, and I really can't see what you can see, but hopefully you can see the rest of the room far away. And as that image from distance far away is coming into this mirror, it's converging, and then standing as a real image from that point, So you should see an inverted, smaller image of the rest of the room as it's far away. One thing about a concave mirror, though, is if you're inside the focal length, then you'll see a non-inverted, larger image of the object in question. So as my hand moves inside the focal length to this mirror, you should see a larger image of my hand as it's reflecting off this concave mirror. Here's a setup of a solar collector using concave mirrors, and all the light over this solar area is, well, actually light is coming in these mirrors over here, and they're reflecting off this central concave mirror, and all that intensity is being focused on the center at this focal point here. So as it's focused on that center, that'd be quite a large intensity, very large power per area at that point, and that's being used and collected for energy. What about diverging or convex mirror? Let's apply our ray diagram to this. Convex mirror is the convex side of the spherical surface is mirrored. Here we have an object in front, and if we had a ray coming into this mirror as if it were to go to the center of curvature on this other side, it's going to hit, at least locally, on the mirror in a perpendicular sense, and it's just going to reflect right straight back out. So any ray that's coming towards the center of curvature on the other side is going to reflect straight back out through that point. So it's going to appear like it's coming from the center of curvature, at least for that ray. Let's say I had a ray coming in parallel. If it comes in parallel, it's going to reflect, and in a local sense, if you were to focus in on that point, you would see that the angle of incidence equals the angle of reflection, and it appears to come from a point which is the focal point of this convex mirror. So a point that is half the distance of the center of curvature, and this ray coming out appears to be coming from that point. If we put these two rays together and we were outside looking at this, we would see that they both appear to converge from a point where these two rays intersect. So this object, this real object, has a virtual image located at this point. The image is behind the convex mirror in this case. It is smaller than the object, and it's got a negative image distance because the image is not on the side of the true outgoing ray. All the real rays are on the side of after they reflected off the mirrored surface. So the image is not on the side of the outgoing ray, hence the image distance is negative. Here's another ray. It's coming right at the vertex of this convex mirror, coming in with the angle, reflecting with the same angle if we treat locally as it being like a flat mirror on that very local scale. And if we follow this reflection back, it actually would pass through that same point on the image. So that ray could be used to locate where the image is as well. We only need two rays to locate where the image is. Here's a fourth one that Ever will print out here. It's coming in as if it were headed towards the focal point, and anything headed towards the focal point is going to reflect straight back out like it were parallel to the principal axis. And if we were to follow that reflection back out parallel on this principal axis, that too would follow through that point on the image. So any two of these rays could be used to construct the location of the image on the convex mirror. Let's take a look at a convex mirror. Here's a convex mirror. and you should be able to see the rest of the room. But in this case, contrary to the concave mirror, the rest of the room is indeed upright. You're just seeing a smaller image of the rest of the room. And same thing with my hand here, even if it's inside the focal point, at least on this side of it. So everything in the room is seen upright and smaller, and that's why this would be a good mirror to use if you're trying to observe, say, the full store. If you had a grocery store or something, a convenience store, and you want to check and make sure that you can watch people so that they don't steal anything, this will show the whole store at one time through this mirror. So the image of a convex mirror will always be upright, virtual, and smaller than the object. And that will be guaranteed for no matter where I put this object in front of the convex mirror. Here's a magician's illusion. Let's say we had an object and we illuminate it, and we have it actually hidden away, but we have a mirror behind here, and we allow that mirror to actually form a real image of the object somewhere else. So if you were looking out over here, you would actually see this real image, and the light rays would be coming from it as if it were a true object. And as far as you know, that could be the object right there. If the resolution is good, you would see a real image, and it would appear to you like the object was actually there. So if you wanted to make this thing disappear, you could have somebody else just move in on this object and cover it up so that the light never makes it to this mirror over here, and all of a sudden your image will disappear. So something like this. You see this fire there, and it's actually being projected there as a real image of a fire that's elsewhere. And so the magician does some movements, and then somebody else covers up the fire, the image disappears, and it looks like he made something disappear in front of your eyes. But it never really was there. It was just an image. Here's another illusion, a famous illusion, mislabeled a holographic device, but it's an illusion where it actually shows an object and a real image of the object, and it appears like you can actually touch that object, but it's not actually there. It's formed in a real image that's not actually there. Here's how it actually looks. It's actually two mirrors, two concave mirrors. And if you put an object in the center here, this object is actually at the focal point of the mirror up above. So as rays come up to the mirror up above, since it's at the focal point of that mirror, they come out parallel from that mirror. And then these parallel rays rain down onto the second concave mirror, which also has the same focal length. And as these parallel rays come into that mirror, they converge on the focal point of the second mirror. Hence, you end up with a real image of the object at the focal point of the second mirror, and it appears like the object is there. It's a great illusion. It's not holographic, but it's a great illusion using optics for the focal points of two concave mirrors. Well worth buying this as a Christmas gift for somebody. That concludes the first lecture of geometric optics in chapter 36.